Surge causes flooding of coast margins during hurricanes, where strong winds pile up seawater and blow it into the land. Surge can also be an unwanted peak of energy in power lines, damaging unprotected equipment. In ocular surgery, post-occlusion surge refers to an undesirable component of the fluidics of phacoemulsification that causes anterior chamber instability. It is a transient shallowing of the anterior chamber that starts when the tip of the phaconeedle becomes cleared of occluding material. The surge phenomenon reduces control and can increase the risk of complications such as posterior capsule rupture and vitreous loss. When the phaco tip occludes, the outflow through the aspiration line reduces, increasing vacuum and approaching the preset vacuum limit. When the occlusion breaks, there is a sudden increase in outflow that creates a void of fluid in the anterior chamber. The inflow line dynamically compensates this void by replacing the fluid that is being removed. The delay between the outflow increase and the inflow compensation creates a transient shallowing of the anterior chamber known as post-occlusion surge. The magnitude of the surge is related to the vacuum level in the aspiration line at the moment of occlusion break. Reducing surge to safely increase vacuum levels would be advantageous by lowering the ultrasonic power required for cataract removal. Significant steps in this direction have been already accomplished. Bubble-free aspiration lines and high vacuum aspiration tubing reduce line compliance during tip occlusion, limiting the surge. Small internal diameters of phaconeedles increase resistance to flow at high rates, limiting the surge. Addition of a small side port in phaconeedles bypasses fluid under occlusion conditions, reducing vacuum buildup in the aspiration line, limiting the surge. Some phaco consoles detect the occlusion status and automatically adjust the fluidic parameters, also limiting the surge. We designed a phacofluidics laboratory to study the post-occlusion surge phenomenon. The objective was to evaluate potential enhancements to current surge suppression technologies in a controlled setting simulating the anterior chamber of the eye. A computer-based system was equipped with several sensors and actuators to perform surge-related experiments. Custom-designed flow meters measured the displacement of a thin disc caused by fluid flow, allowing to record flow rate in real time. Pressure transducers and flow meters were placed at different locations in the irrigation aspiration circuit. Specific software was developed to analyze the fluidic parameters and to operate the actuators interacting with the flow circuit. A special chamber was constructed to simulate the anterior chamber of the eye and to receive the tip of the phaco handpiece. A solenoid-driven plunger was arranged to obstruct and clear the tip of the phaco needle inside the artificial chamber, simulating the occlusion conditions that occur during surgery. The Alcon Legacy and ASCRS 600 phaco units equipped with high vacuum tubing and different phaco tips were used for the experiments. After occlusion break, the pressure drop in the aspiration line recorded at the handpiece level junction occurs very early and is very steep. Reduction in signal amplitude and increased delay in signal detection is observed at the distance of the measurement point and the handpiece increases. Pressure changes inside the rigid artificial chamber were considered the in vitro equivalent to the surge phenomenon observed during surgery. In this setting, a transient negative pressure wave occurs following occlusion break. However, the real eye is not a rigid structure like the artificial chamber testing device. Instead, it possesses a negative compliance that allows the walls of the anterior chamber to collapse when the internal pressure drops. This collapse represents a volume shift and should be expressed in volume units. We believe a more realistic approach to surge determination is achieved by providing an artificial anterior chamber that is collapsible like the real eye. Inspired in this concept, we improved the experimental anterior chamber, attaching a negative compliant fluid container. In this way, an exact measurement of the collapse volume could be quantified and digitized. Also, the collapse volume could be visually followed. The collapsible container could be optionally connected to the artificial anterior chamber by opening a valve. In this way, post-occlusion response can be evaluated in a pressure domain when the valve is closed or in a volume domain when the valve is opened. The pattern observed in the pressure domain measurements consists in a surge-induced negative pressure transient in the anterior chamber following occlusion break. Chamber pressure undershoots from a positive value determined by the bottle height to a short negative peak below atmospheric pressure. Flow meters show that on occlusion break, aspiration flow is instantaneously followed by irrigation in the rigid experimental chamber. flow through the anterior chamber can shortly increase to a peak flow rate that can double the preset aspiration rate in the phaco console. Soon after this flow overshoot, flow rate returns to the console preset value. The outflow over rate is explained by fluid displacement to the aspiration line contracted by vacuum during occlusion. Fluid displaces to cancel pressure differences after occlusion breaks. Outflow and inflow occur simultaneously because the rigid walls of the anterior chamber transmit vacuum from the aspiration line to the irrigation line as if it were a single compartment. By opening a valve, the collapsible container is connected to the anterior chamber, adding negative compliance to the fluidic system. This allows to study the post-occlusion events in an in vitro environment that is closer to the real-eye situation. A comparison of the post-occlusion surge events observed with the compliant anterior chamber reveals different characteristics to the pressure domain surge profile. The negative pressure shift observed in the anterior chamber does not undershoot to an absolute negative pressure value. Instead, it becomes flat near atmospheric pressure at a level corresponding to the positive pressure of the water-filled chambers surrounding the collapsible membrane. Duration of the surge is longer, as inflow is delayed with respect to outflow as shown by flow meter data. These differences are explained because there is a buffering compartment that prevents direct transmission of vacuum between the outflow and the inflow lines. With the compliant chamber, we can detect an anterior chamber volume fluctuation participating in the post-occlusion surge response, comparable to the real-eye intraoperative surge manifestation. This volume fluctuation information adds a new dimension to the post-occlusion surge understanding and can help to design better post-occlusion surge handling strategies. Analysis of flow and pressure data obtained in vitro during the post-occlusion surge allowed us to work on a concept that could improve the post-occlusion brake response of phaco systems. This device would allow a safe use of higher vacuum levels, reducing the amount of ultrasonic energy. The same device could improve the efficiency of Venturi pump-equipped phaco systems by providing the missing flow rate control. The system consists in a computer-controlled flow regulator located beside the phaco handpiece. Prototypes were built using fast-acting solenoid valves and stepper motor-actuated valves. The solenoid valve is operated on a pulse-width modulator scheme using a programmable time base and a variable duty cycle. Operation of the solenoid valve produced noisy recordings of the post-occlusion volume fluctuation detectors. In these cases, video photographic measurements of the surge-related volume shift were used for data collection. We could observe a significant reduction in surge-related volume shift when the flow regulator system was in operation. A fluid bypass port set in parallel with the solenoid valve dampened the shock wave created by the valve shutter. Also, non-ABS phaco tips showed a significant reduction of the post-occlusion surge when tested using the flow control system. A completely different fluidic pattern was observed with the ASCRS Venturi phaco, mainly characterized by an instantaneous pressure rise after occlusion break. Our control system could add an overflow control for Venturi pump phacos. We have constructed a phaco fluidics laboratory that allows an objective comparison of post-occlusion surge performance between different phaco equipment. We provide an attractive workbench for experimenting in improving post-occlusion surge handling strategies. We demonstrate that the most accurate aspiration line pressure measurements are performed near the handpiece. We use a negative compliance artificial anterior chamber for closer understanding of the events related to the occlusion brake response. We introduce the concept of measuring surge both as a pressure transient and as a volume shift phenomenon, providing a more realistic research environment. We propose that the transfer function between pressure and volume fluctuations on occlusion brake will vary according to the compliance characteristics of the chamber under study. We describe a flow control system that can improve the fluidic behavior of both peristaltic and Venturi pump-based phaco systems. We believe that systems with improved post-occlusion surge response will allow safer use of high vacuum, leading to reduced demand for ultrasonic power. We expect that further research will teach us if the proposed flow control system may have a place in the cataract surgery of the future.